I'm Dr. Khanlou. I'm a neuropathologist. Today we are going to talk about a second portion of our skeletal muscle studies, studying the normal and compare the abnormal to what we know. If you followed the first series, you're familiar with this table. These are the studies that we perform systematically on every single muscle biopsy that comes through our lab. And that's because we want to have a good view of the morphology and components of the myofibers and also overall function of the skeletal muscle and see if it's normal or not. Today we're going to focus on the fiber types in the skeletal muscle. The skeletal muscle biopsy would allow us to see whether the muscle that comes from the patient has the appropriate number and composition and distribution of the types of the fibers that we need to find in that specific muscle. By that I explain. First of all, let's just do a brief study of what we do as a testing to identify the different types of the myofibers. By using the myosin heavy chain and by using different series of the reactions at different pHs, whether alkaline, basic, or acidic, we are able to differentiate two major types of the myofibers in the skeletal muscle. All skeletal muscles in the body have are composed of type 1 and type 2 fibers. Their distribution is always regular and in a mosaic pattern. And they may not be necessarily the same number in every single muscle. I'm going to explain why, but they have to be there. You cannot have a group of muscle with only one type of fiber and another group with another type of the fiber. Different activities or lack of activity or different circumstances, they can affect the health and composition of the different myofibers in the skeletal muscle, but they both have to be there unless there is pathology and a disease affecting it. So to that extent, we need to study these types of and distribution of the myofibers type 1 and type 2 by using the ATPase or myosin heavy chain stains. What are those myofiber types? We have type 1 fibers. Type 1 fibers are the ones that do not get tired very easily. They are rich in mitochondria. They use lipid as a substrate, and they are for sustained activity. Muscles that you sit on are rich on type 1 myofibers. As opposed to type 2 fibers, which are your sprinting muscles, they actually are used for really for fast twitch and fast activity for a short period of time. So those, they do not really have time to go through all the enzyme reactions and respiratory chain in the mitochondria and use the lipid to its best. So they would use glycogen instead. They would still have mitochondria, but not as many as type 1 fibers. Now, when looking at the basic morphology on hematoxin and eosin stain or Gomori, generally we do not see any difference between any myofibers distinguishing them as being type 1 or type 2. We have to really go and look into the composition, myosin composition, and also the organelle composition of the myofiber to be able to tell whether they're type 1 or type 2. The ATPase reactions are really neat studies because they allow us to, of course, distinguish the type 1 fibers and type 2 fibers and subtypes of type 2 fibers. And even fibers that are immature and regenerating, they would allow us to see those as well. But we have to do them at different pHs, and that's fine. And what a normal muscle that shows is a mosaic pattern. That's what we see here. Or maybe you would like to call it a checkerboard pattern. You would see that the distribution is quite, regular, and you have some type of fibers that are of one color, and then other fibers that are darker color. And so this is what you want to see in a normal muscle. You do not want to see a lump of light fibers on one side and lumps of dark fibers on one side. That would not be normal. You do not want to see only one type of fiber. So this is very neat because it allows you to really assess the number and the distribution of the different types of fiber in a skeletal muscle that is weak and a biopsy to be studied. Here we discuss very briefly the methodology. You can go through it, and if you would like to ask questions, you can email me at some point. And basically, it's the end part is that when we are doing these reactions at different pHs using the ion exchange, we would be able to differentiate one fiber over the other. At acid pH, it would be type 1 fibers that would show up much darker, and at alkaline, your type 2 fibers would show up at being dark. People, they can use in their laboratory different counterstains and different colorimetric reagents, so they can come up as black and white or brown and light, or again here like pink and purple, or dark and light. Anyway, that's the goal of this testing. Here we are looking at an acid pH of a myosin heavy chain study, and obviously the fibers that are dark are type 1 fibers. That means that they are rich in mitochondria, rich in lipid, and you can actually see their distribution throughout this myofiber, the fascicle. And also you can see the lighter fibers. What does allow, it's not only to see the distribution of these fibers, their number, but also their size. You can possibly see some maybe type 2 fibers that are smaller versus others that are normal in size. So you can really determine whether one type over the other is showing abnormality, or the abnormality is affecting equally both fiber types. Here we have the reverse reaction, where we have the alkaline pH, and of course there here we would have our type 2 fibers that would be dark versus type 1s that are light. And again, that gives you an idea of the size and distribution of type 2 fibers. And you may say, why do we do that? But because different conditions, primary muscle disease or denervation, they would affect myofiber types in a different way. That also their distribution and how they aggregate together, it also may give an idea about, for instance, in denervation, of the chronicity and how the body is reacting to correct the pathology, and we will see examples of it. If we compare, this is basically the same picture. If we compare both, you would see the alkaline, where type 2 fibers are darker, and the same fiber you can see in acid is lighter. An example of pathology, using ATPase at pH 9.2 alkaline, we would expect our type 2 fibers to be dark and type 1 fibers to be light, and this is what this slide is showing. But notice that while your type 1 fibers are practically of normal size, numerous type 2 fibers are present and are very small comparatively. In a lot of conditions, there is a type-specific atrophy. Type 2 fiber atrophy is also a condition that can affect some people with different diseases. For instance, patients with diabetes, patients who have been wheelchair-bound, have not used their leg muscles for a long time, patients who have received steroids for a long time for variety of reasons, they would develop type 2 atrophy. And this type 2 atrophy can make the patient weak. Well, you may say this is a very non-specific thing then, and you see it in the different conditions. It is true, but it can be also very specific. It can be, for instance, the only sign that a tumor is declaring itself. How? Well, the tumors, they have ways of affecting many organs at distance of themselves, including skeletal muscle, and sometimes severe type 2 atrophy can be the only manifestation of it, which shows how complicated the neuromuscular pathology can be. So here you have a very nice example of type 2 fiber atrophy. If you compare it to the normal muscle, you would very clearly see that difference in size between the type 2 fibers. Here you have practically the same size between the among the myofibers, whereas on the other one, type 2s are much smaller. we have a different set of pathology on this slide. Now take a minute or take a second and look at both slides. On my right side, we have a normal muscle. It doesn't matter what type of ATPase we're looking at here, because what I want you to look at is the pattern that you were seeing here and what is normal and what is abnormal. And then look at this skeletal muscle that has gone through an ATPase reaction. The difference there that you see is clearly there, and you have a very nice distribution of type 1 and type 2 fibers in the normal muscle. You don't see lumps of one over the other. But when you look at this one, you can see an area that's exclusively composed of one type of fiber. That is called fiber type grouping, and we will discuss it a little later and explain to you why this happens. It's not normal. It is not normal. Why it happens? It can happen in neurogenic conditions, and it can happen in subset of primary muscle diseases. So again, by studying the type of fibers, their distribution, their grouping together, or their difference in sizes, we can have an idea about what is affecting the skeletal muscle and the patient. We are going to jump to the hydrolytic enzymes. And the reason because there would be a combination of studies of ATPases and a subset of hydrolytic enzymes called non-specific esterase to give you some neat examples of pathology. Focusing on non-specific esterase, this is an enzyme and this is a reaction that we use to assess the state of innervation of the skeletal muscle. If the innervation of the skeletal muscle is disturbed, whether it's happening at neuromuscular junction, at end place literally, or whether it's happening on an axonal level, at more plexus level and even higher motor neuron level, well, NSE would help us to see it. Remember our denervation slides from the prior lecture, or go back to it and review it. You have the normal histology, polygonal shaped cells, practically of the same size with the minimal variation. And then you have your angular atrophy. And we said that angular atrophy generally happens in denervation. Well, it is true that morphologically you can see it very nicely in a skeletal muscle biopsy that is well preserved and has only a few of them, or maybe a good amount of them. But when you look at non-specific esterase, it would give you another idea about the severity of the neurogenic changes in the muscle. Here we have on this slide normal non-specific esterase, and it's neat because you would see the same kind of, it's the first enzyme when you're studying, looking at the slides, that would show this mosaicism appear among the myofibers. You would see darker myofibers and lighter myofibers. This thing is not intending to show you myofiber type distribution, but somehow it kind of reflects it as well. This is normal. You can see lighter fibers and a little bit darker fibers, normal size. Here we have another, on the right hand side, another type of NSE, another NSE from another biopsy, where you would see these darker areas. And these darker areas are the basically motor end place. This is where the axon terminations ends on the myofibers. And it's a neat and incidental finding in skeletal muscle biopsies, and that shows that really NSE really working in identifying the neurogenic health of the skeletal muscle. Here we are dealing with a patient who has denervation. We see the angular fibers, the arrows are pointing to them, and you can see that not only these angular fibers, by morphology they're standing out, but their color is much darker and they are reacting much more intensely with non-specific esterase than the other fibers. So you would again may say, why are we doing it again? Because we had the morphology. Well, a lot of times we are showing you the best examples. A lot of times these fibers, they can be very tiny, and actually the denervation can be much more severe than we are seeing on the basic morphologic hematoxin irisin. So non-specific esterase not only proves that these fibers are denervated because they are hyperactive with the enzyme, but also shows the severity of the denervation, and it also is showing that the denervation is acute and active and ongoing. So this patient really, whether at the motor neuron level or axonal level, is having an injury. Again, you can compare it to normal, and you can see very nice distribution and all the morphology of the myofibers on this is very polygonal compared to your angular fibers. The skeletal muscle biopsy shows severe disease. It shows severe disease because when you look at it and systematically go through the steps that we discussed on the first lecture, first of all, you can see there's tremendous fat in the perimysium, which is not a good sign. You see some separation in some areas of the endomysium. You can see myofibers that are angular and very atrophic, and myofibers that are very, very large. You can also see the morulae or nuclear clumps. So basically what we're seeing is fiber atrophy, and by morphology and the way it looks like it's denervation. And because there is scar tissue which is manifesting here as the fat replacement in the perimysium, we know that it's been going on for some time. Another thing that shows the severity of the disease here is the fact that we see a lot of these angular fibers grouped together. Basically what we're seeing here is grouped atrophy. Now when we see grouped atrophy, we know that it's not just one axon that it's not doing its job. We know that's a really large axon, a large trunk that is not doing its job, or the motor neuron disease. If the clinicians are sending a biopsy and telling you we suspect motor neuron disease or ALS in this patient, this biopsy would be consistent with it. But if they do not give us any information, we can tell them there is severe, chronic, grouped atrophy of denervation. We can't really tell them this is motor neuron disease versus another more peripheral disorder. If we do non-specific esterase in the biopsy that I just showed you, of course we are going to see zones of atrophic fibers, of which many would be very active or hyperactive with non-specific esterase. It happens so that in this patient, when we did ATPases to see the distribution of the myofibers, and I'll explain it to you in a little bit why we do that, we saw this pattern. Lumps of one type of fibers on one side and lighter fibers in another side. Grouped atrophy of denervated fibers. And another term that we use on ATPase is grouping, which is very different from grouped atrophy. Grouped atrophy refers to smaller, thick fibers. Grouping means that same type of fibers are lumping together, and that's not normal. But it signals that the body is trying, the muscle is trying to compensate for what it has lost. This is a great picture from Color Atlas Muscle Pathology. If you can find and review it, that would be great. Basically, what we are looking here in number 1 is a normal state of innervation of the skeletal muscle. You have motor neuron A that is sending axon A to light myofibers. You have motor neuron B that is sending axon B and influx to the darker myofibers. It is, the theory is that in real, the motor neurons determine the type of the myofiber that is attached to them in the end. How, we don't really know about it, and it's been studied. But this is how it goes. Motor neuron A innervates type 1 fibers, for instance. A motor neuron B innervates type 2 fibers. Let's just say by pathology, by disease, one of these motor neurons is basically injured, or maybe the axon injured, or the end plate, somewhere it's injured. So what happens is that these fibers that are attached to this one are gonna, of course, atrophy because there's nothing to pump them and keep them healthy. So what happens, the nature generally likes to compensate, likes to regenerate. So because this motor neuron here is gone, this one is going to take over. But this one produces or makes type 1 fibers, or any type of fiber, any specific type of fiber. So whatever fiber is going to be attached to this is going to become the type that this motor neuron is controlling. This is the grouping that we see in reinnervation and that we saw in this picture over here. And again, if this motor neuron is going to go away, it's this one that's going to take over. And we will see another type of grouping, fiber type grouping. Grouped atrophy, fiber type grouping, denervation, reinnervation. And at some point there would not be any reinnervating potential, and basically the whole muscle is going to become atrophic and not go back to its normal. And you can imagine that if the normal distribution of the muscle is this muscle, even though plumped up in number and in volume, it's not going to function well. We all know about amyotrophic lateral sclerosis or ALS or motor neuron disease, and we have this iconic figure to represent it. And the pictures that I showed you basically could have been muscle biopsies from any patient with motor neuron disease, at least at the active phase, because when the muscle becomes end stage, then there is not much into it, and we will see examples of it. Now, among hydrolytic enzymes, we have other sets of studies that we can do, and those studies generally are aimed to show the turnover in the skeletal muscle, meaning that if there is an injury in the skeletal muscle, how severe that injury is, and is there any potential for regeneration. So you have to know. We can have an idea by using basic morphology, but we prefer using specific reactions to show us really the regeneration and degeneration. One of the ways of looking into the reactivity of the skeletal muscle and also regeneration is using alkaline phosphatase. Alkaline phosphatase is very, very reactive with reactive fibrovascular core. Muscle biopsy, skeletal muscle is very richly vascularized because obviously it's working all the time, it needs supply. And these vessels at normal status quo, they would be not expressing too much of alkaline phosphatase. But when they are abnormal and they are attacked either by antibodies or when they are injured themselves, they would have a lot of activity and show a lot of activity on alkaline phosphatase. Normal alkaline phosphatase is our yellow state on a set of studies of the skeletal muscle. And you can see that in normal, really understated microvasculature is really seen, and that would be what we would see in a muscle that has not been injured or is quiet or disease is controlled. However, on this side, you would see the same stain in a muscle that has, in a patient that has dermatomyositis. Remember, we said that in dermatomyositis, the fibers on the side are injured, whereas the fibers on the center not so much. And you can see the intense reaction of alkaline phosphatase around these fibers. Not only that, but intense reaction in the perimysium of the fibrous tissue and also the vascular tissue. This alkaline phosphatase reactivity shows not only the intensity of the disease in the skeletal muscle, but also shows the potential for turnover. Is there any potential, is there any regenerative features in this? Because sometimes regenerative fibers, they can actually show up on alkaline phosphatase as well. Now, for regeneration, you have to have degeneration, right? And that's what we assess with acid phosphatase activity. Many of the way I am explaining these studies to you is as if the one test is done to show you just one thing. It is true, really, it has been developed for that. But over the years, we have realized that many of these stains, they can kind of cross-react with other things, and we can get much more information from them, and that's another reason why we do it. And patterns, different patterns combined together can tell us what is affecting the muscle. But just purely for the sake of simplicity, we can say that acid phosphatase is the reaction that we use to show the degeneration and active degeneration of skeletal muscle, particularly when the fibers are dead and the cleanup crew is coming to clean them up. In normal state, our pink acid phosphatase reaction, or at least that's the colorimetric reagent that we use in our lab, would be kind of understated. The nuclei would have a brown hue. The rest of the cytoplasm would not show much of a reactivity. But when the lysosomal activity is heightened, and when there's a lot of digestive activity and phagocytosis in the muscle, obviously in the acid phosphatase we can clearly see it. In the background of the pink, no reaction, we will start to have all these macrophages that are coming to either clean up or attack, but it can be part of the first crew that attacks the muscle, they can be part of the crew that comes to signal regeneration, or they can be part of the crew that comes to clean up the muscle. At any rate, we can see them very clearly on the skeletal muscle if there is anything going on. Here you have a myofibrous totally invaded by the macrophages because they're cleaning up a dead myofiber. So by using the alkaline phosphatase and acid phosphatase, we have a balance to establish between the regeneration and degeneration. And it kind of gives you an idea about, okay, this muscle is degenerating too much. Is it because it's an active phase of disease? Is there going to be potential for regeneration? Or this muscle is degenerating and there is no regeneration in it at all? And also, it gives also an idea about how severely active the disease is by using both studies. We are going to just make a very simple review. If a muscle cryosection is stained with acidic ATPase, what features will be visible? Peripheral nucleation. Do we see them only on ATPase? I don't think so, because we can see them very neatly on H&E. Type 2 muscle fibers. Well, remember that ATPases are developed to differentiate type 1 and type 2 fibers. Now we have to figure out whether acidic is for type 1 or type 2. We can go back to the slide and study it. Adipose cells, they show up in many of these slides. I have to say that the best way to see the adipose cells or the fat is the paraffin tissue, because fat does not cut very well on fresh frozen. So a lot of times we don't see it, they fall off from it basically. So no ATPase is not developed to see fat. And grouping of the fiber types, it's true. We can actually, if there is any abnormality, we can see it. So acidic ATPase is for type 1 fibers. If there is any grouping of the fiber types, can also be seen in this, with this test. The set of enzymes that we use to study the mitochondria and the skeletal muscle are NADH, complex 1, SDH, complex 2, and cytochrome oxidase, which is complex 4. Now, you may say, why all of it? Because there are differences between where these enzymes are coded and provided to the mitochondria, and depending on which one is lacking, we may or may not see or we may or may not be able to identify mitochondrial abnormality. For instance, NADH is also used as an enzyme by other organisms in the skeletal muscle. What if it's them that are not normal, basically? So we want to differentiate between mitochondria and, for instance, the tubular system or RER. Whereas we know SDH is specific to mitochondria, so if it's abnormal, then we are pretty sure that the mitochondria are not normal in the skeletal muscle. Let's just talk about mitochondria in the skeletal muscle for a second. Mitochondria are really the energy machine, the oxidative enzymes that are contained in the mitochondria. They are bound into mitochondria by a double membrane. This is a skeletal of normal mitochondria on the electron microscopy. You can see the internal cristae and the double membrane. Generally, they are distributed where the action is, meaning around the nucleus on the side or around the Z-disc where the contraction machinery basically is at work and you have the mitochondria all over. Now, using the enzymes that these mitochondria generally use inside themselves, we want to have an idea about their morphology. Are they normally distributed? Are they a normal number? And if their morphology is normal, is there any abnormality in the cristae or the membrane or whatnot? Why do we think that STH is still useful when we have NADH? Or why we think that we still need cytochrome oxidase if we have the other two? As we said, NADH can be used by other organelles. So if NADH is abnormal, really on a reaction, we cannot tell for sure that it's NADH, this belongs to mitochondria or not. Whereas STH, it's only used by the mitochondria. And why is it that when a mitochondria is abnormal, we would still use STH to localize it or to visualize it? It's very neat because mitochondria, it's true that there's this fantasy about mitochondria, how independent they are. And some people, even they had considered maybe they've been parasites of the much more complex organisms such as ours that happened millions of years ago. But it's not so, because we still know that more than 90% of the proteins that mitochondria use are still encoded by genomic DNA. Mitochondria have a DNA and they provide for a subset of enzymes that they use themselves, but sometimes not entirely and sometimes not at all. And 90%, more than 90% of their proteins can come from the, is coded by nuclear DNA. And STH is one of them basically. STH is coded by nuclear DNA. So regardless of mitochondria sick or healthy, they're going to always have STH to use. And this reaction of the STH with normal and abnormal mitochondria is going to give us a pattern on the histochemistry that would say this fiber is not normal because the mitochondria is not showing up normally in it. Here basically what we are showing is that we have the complex 2 here, and you can see that the number of units of complex 2 that are coded by mitochondrial DNA, 0. So that is why it's the best enzyme to study the mitochondria, because it's specific to mitochondria in the cytoplasm, and also regardless of mitochondria sick or not, it's going to always have this enzyme provided by the genomic DNA. We had an example of ragged red fiber myopathy. This is a broader view of it. You can see these ragged or cracked marble looking fibers. We can compare the morphology of the cytoplasm of these fibers to the more normal ones. They can be smaller or of normal size, but they definitely don't look normal. These areas of indentation and accentuation, whether inside the cytoplasm or under the sarcolemma or membrane, are abnormal aggregated mitochondria. This is a larger view of it that you can see here. This is a normal NADH in a normal muscle. Again, because the amount of mitochondria in type 1 and type 2 fibers is different, obviously you're going to see the same mosaic pattern on NADH than in ATPase reactions, but these studies are not developed to differentiate type 1 versus type 2 fibers, even though they provide information about them. Normally you can see type 1 fibers that are uniformly or very homogeneously dark, and then type 2 fibers that are not as dark because they do not have as much mitochondria in them. On this side, we have succinate dehydrogenase complex 2 on a normal muscle. And again, we have a mosaic pattern because type 1 fibers are going to have more mitochondria. Now, what happens if we are looking at the ragged red myopathy case? Well, you would see a very different pattern of STH. Now, some fibers, they would be normal, that's fine. But some fibers, they would show these accentuation in subsarcolemmal areas. These are the mitochondria basically that have soaked up or that are using succinate dehydrogenase. But because they're abnormal, the enzymes in it is going to show up in a very abnormal way when we are staining it with it or reacting the tissue with it. Whereas a muscle fiber that has normal distribution and normal morphology of the myofiber will not have the same appearance on SDH reaction. Now for sure we know mitochondria are abnormal. That being said, it also a big correlation with what clinicians are telling us to say whether this is primary again disease or combined with other stuff that we may find on the muscle biopsy, we can say, well, this is secondary to what we're seeing. For instance, some autoimmune disorders, they can have mitochondrial abnormalities. Electron microscopy is the way of to prove that the mitochondria are abnormal. And basically, what we do is that we take the same muscle that originally has been processed for fresh frozen tissue and histochemistry. It has been also stored in resin, and that one is subjected to electron microscopy, blown up many, many times, 10 to 20,000 times, and we can see actual mitochondria in this one myofiber. This is your myofiber, and those areas of accentuation are represented here by many mitochondria. Not only there are too many of them, this is not normal distribution. They differ in size. Some of them are larger, some of them are much smaller. But if we look at inside and compare it to normal mitochondria, the internal structure is absolutely abnormal. So this is an example of mitochondrial myopathy, or a myopathy in which mitochondrial abnormality is a component of the disease. We are going to have a review question, and you can take a few seconds to think about it. Why are pathologists interested in looking at the mitochondria of muscle cells? Mitochondria grouping patterns can reveal DMD, or Duchenne muscular disease, muscular dystrophy, sorry. Well, as far as I know, that's not the typical thing that we would see in Duchenne muscular dystrophy. Mitochondria are not known generally, primarily, to be affected in Duchenne. Mitochondria are active at low pH staining. I don't think that has anything to do with the pH staining at some point, at least not in the studies that we do. And I don't see the reason why they would necessarily do a pH staining if there is no reason to suspect mitochondria. Mitochondrial membranes are damaged because dystrophin proteins localize to mitochondria. That is not true. Dystrophin is a component of the membrane of the myofiber itself, and also has a component in the cytoplasm. It extends to it. But basically what we are looking in skeletal muscle is to study the mitochondrial function and to determine whether its function is normal, whether the muscle is suffering from mitochondrial abnormalities or not. Now, our study does not end by proving we have abnormal mitochondria in the skeletal muscle. When the question is whether this patient has a mitochondrial myopathy, which is a form of metabolic myopathy, then we have to further study the muscle by going and actually measuring the enzymes in the muscle. And that's the portion of stored fresh frozen muscle in the freezer that's going to be subjected to another set of study, which is called biochemical study, which is not part of these lectures. But I wanted you to know that when we are looking into mitochondria, we have to go all the way to study a quantitative study of the enzymes. This ends lecture number 2. I see you at lecture number 3 about Duchenne muscular dystrophy.